everyone, and thank you so much for joining us today for the Quantum Speaker webinar series hosted by HRC's Global Quantum Working Group. We are very excited to welcome Alex Khan to speak with us today. Mr. Khan is an advisor, entrepreneur, author, and educator in quantum computing. He's the CEO of ZebraKet, a Canadian startup in leak detection and sensor optimization using quantum methods and AI. Mr. Khan is the author of Quantum Computing Experimentation with Amazon Brackets, and he has also been recognized by the Quantum Daily as one of the 126 advisors shaping the quantum computing industry. There may be time for questions at the end of the presentation, so please feel free to utilize the Q&A feature or raise your hand and you'll have an opportunity to speak. And with that, Alex, we'll hand it off to you.
All right, thank you. I'm going to share my screen. All right, are you seeing it?
Yes, we are.
Okay. All right, so good afternoon, everyone. I'm going to go over some of the experiments and use cases that I've been involved in over the last 4 years. And I'm just going to skim through most of them. And I will show some equations, though I'm not going to get into a lot of details with the equations. The main purpose of the presentation is to give some context, some hands-on experience on the size of problems that can be solved with different kinds of quantum computers. So let's get started. So as an agenda, I'm going to go over various methods to solve combinatorial optimization problems, give an idea of the current hardware and algorithmic capability. We'll go over some use cases, including financial portfolio optimization, COVID lockdown optimization that I did, inventory replenishment, and sensor placement. And then in that process, you'll see some visualization of the energy landscapes, QA/OA results, which is the quantum approximate optimization algorithm, which is needed if you want to do optimization on gate quantum computers. So here are the different kinds of quantum computers or annealer that are out there. There are superconducting, like Google, IBM Q, and Rigetti. There's also superconducting annealing, which is D-Wave. We also have the trapped ion systems, IonQ and Continuum. There's photonic systems like Xanadu and PsiQuantum. There's neutral atom systems like QERA, Pascal, atom computing, and whole quantum, which is inflection. And then there's various simulators. Amazon Bracket has simulators like SV1 and TN1. IBM, Google, all of them have various simulators. There's actually a list of hundreds of simulators out there. So quantum computers are obviously using different quantum properties like electronic spin or the energy levels. They're in the superconducting qubits. There's a loop of superconducting current, and the direction of the current becomes the qubit or the state of the qubit 1 or 0. And then with photons, you use polarization. So these are properties that different quantum computers are using to do their calculations. So I wanted to basically mention that there are two types that I'm going to be discussing, the annealing and the gate quantum computers. In the annealing computers, you basically put your problem, Hamiltonian or the equation, into the system. It creates an energy landscape, and then the annealer's job is to find the minimum energy. So it does the number of sampling. It uses properties like quantum tunneling to eventually find the lowest energy value. And it's a single purpose machine. Its job is to, if you put your problem on it, give you the minimum value. Universal or gate quantum computers are those where you have logical gates. These are quantum gates where we do rotations on the qubits. They're supposed to be able to do any kind of calculation. So they are general purpose machines, and there are various algorithms that we use. I'm mostly going to be going over QAOA, which is the one that I use. There's also other algorithms like Shor's algorithm and Bernstein-Vazirani, which we're not going to be talking about over here. So for context, I just want to give the landscape of how problems can be solved on quantum computers. It's a way that I can help give some context of the different use cases that I'm going to go over. So at the bottom over here, we've got the gate quantum computers. As you know, that they are still kind of limited in the number of qubits. There's errors. There's some of them have full connectivity between the qubits, like the ion traps. But then there's others that, like the superconducting qubits, like Rigetti and IBM, which don't have full connectivity. So, so those are the gate quantum computers, and after that, we get into annealers and other solvers, like the digital annealer from Fujitsu. There's a Quantum Computing Inc.'s Dirac system. There's D-Wave's 5,000 qubit system. So these are basically annealers, or they're able to take a QUBO problem, you put it on there, and it'll find the minimum energy state. You can see that the number of qubits are increasing. So you've got in the range of 5,000 to 10,000 qubits or variables that you can put on there. Each of them have their own nuances. Even though D-Wave has 5,000 qubits, it's not fully connected. So because of that, you can probably put in a 140 variable problem on there if it's a fully connected problem, or a graph that is fully connected. So going further, if our problem size increases to 50,000 or 100,000 qubits, we are getting into a range where we have to use a D-Wave CQM model or D-Wave's binary quadratic model. This is not necessarily quantum. These are hybrid systems, and they use certain quantum and classical calculations. So question, is QCI Dirac fully connected? I believe it is fully connected. I mean, it has its own, they call it an entropy system. And I believe that each qubit in that is connected to every other one, but I'm not familiar with the technology that they use to actually run that. Okay. So let's go over the QAOA, or the quantum approximate optimization algorithm. Keep in mind, we're now looking at the gate quantum computers at the low level in that diagram at the bottom over here. So the capability depends on the number of qubits. What I like about QAOA is that the number of variables is the same as the number of qubits. So if you have, for example, IonQ's Harmony, which is an 11 qubit system, you can put an 11 variable problem. These would be binary quadratic problems. They can't be more than quadratic. And you can see this would be an equation that would represent an 11 variable problem. This is the matrix form of it. So we can take this matrix, we're trying to find the minimum value of this function by setting the different variables to 1 or 0. So there's a combination of variables, and these are binary variables that will give the minimum energy value of this function. So what we do is in QAOA, there is a process of embedding your problem in a quantum circuit, which is called the problem Hamiltonian. And then there's an X-gate function, which is called the mixer function, that basically rotates the qubits. And so if you do it the right way with the right parameters, you will get, the whole goal is to increase the probability of that minimum value. So this is what I'm showing over here, that I sample the parameter landscape. And so there's basically two parameters. One is the problem parameter, one is the mixer parameter. So you can see over here the 0.1 to 0.7, that's one of the parameters, and then 0.1 to 0.7 is the other parameter. So in this case, it's not a very complicated problem. And I'm finding the minimum energy of the function at minus 2.5, which is actually the minimum of that function. So pretty much any parameter gives the minimum because I'm sampling 2000 times, not a complicated problem for these systems. So here you can see that if I use a parameter of 0.7, 0.7, which is down here, I'm not actually helping find the answer. You can see the answer is way at the bottom over here, and the probability of that answer hasn't been increased. But if I use the right values, like 0.4, 0.5, which is somewhere in the middle over here, the probability of that minimum value, the 2.5, increases dramatically. And so I'm going to sample it or find it more often. So this is important because in this case, it wasn't that complicated, but as your problem gets larger, you want to be able to really increase that minimum value. So here's some sample results I got with the local simulator, which just runs on my laptop. I ran these all 1,000 times, so the 1,000 shots or 1,000 measurements. And the minimum answer of 2.5 here showed up 9 times. With the IonQ device, it showed up once, or at least showed up, but you want to have a higher probability there. And then with Rigetti, the minimum energy of minus 2.5 showed up 2 times. So that's with 1,000 measurements. Again, if you have the right probability distribution, the more you measure, the higher the probability of finding the right answer. Okay, so here are some more tests that I did with more sampling. I've got 5,000 samples. You can see that with the local simulator, it's really increasing that probability of the low value. I tried IonQ Harmony again, about the same result, but then I tried IonQ Aria, and it really did increase that minimum value, almost like the local simulator. So IonQ Aria did really well in this case. So question is, are these a NISQ or error-corrected number of qubits? So with the local simulator, obviously that's accurate. These devices, I'm just using the devices without doing any error correction. So you can see if they're doing some internal error correction within the system, then I'm not sure how exactly they're doing it, but these are very good results. Okay, so another method we are working on is rather than doing this parameter optimization and going back and forth between classical and quantum, there are other methods. Here is just basically an example of a method that we are calling fixed point adaptive Grover optimizer. So Grover's algorithm does a search, and if we give it the right Hamiltonian, we're looking for this system to find the right answer and increase the probability of the right answer. So I don't want to go into a lot of detail here, but we are working on this algorithm, and this would be basically a quantum algorithm that finds the optimal answer without having to look for parameters or go between classical and quantum. Okay, so I'm going to move a little faster. So with financial portfolio optimization, we are now beginning to look at that B section in the middle where we need more qubits. You can do financial portfolio optimization with 20 qubits, but then you're looking at 20 assets, which isn't a very interesting problem. So here, when we start getting into financial portfolio optimization, we are able to take, basically Sharpe ratio, and you've got the expected return on top, and then you've got the risk at the bottom. We can't put this equation on a quantum computer, so what we do is we have to convert it a little bit. We convert it into what is called a QUBO, which is a quadratic unconstrained binary optimization problem. You can see that we have to convert it in such a way that you've got the risk on this side, you've got the risk which is plus or positive, and so that will hurt, that's higher energy. These systems look for the low value, and so the minus over here is the return. You've got risk minus return, and the more return you have, the more negative your value is going to be, which is what we're looking for. So we wrote this paper over here. It's been out there since 2020, and it's a very easy problem. So it's easy to actually do on an annealer. We were able to basically try different methods. With D-Wave, you can see comparatively, we were able to solve this problem in a short amount of time. Genetic algorithms did slightly better, but I mean, D-Wave was in the ballpark over there. And this is the plot of the efficient frontier, where you've got the standard deviation on the x-axis and the expected return on the y-axis. The classical results are the the yellow ones. Quantum, so using D-Wave, we were able to extract by sampling the red values over here, and then the blue values are the ones from the genetic algorithm. So very good results, very comparative, and we could do 60 assets. We did go up to 100 assets as well, so you can optimize 100 assets. Okay, so another example is COVID optimization. Again, we're still working with the D-Wave annealer at 5,000 qubits. Those problems can be solved in these as well, but different systems have their own errors and intricacies that you have to be able to work with. So here we looked at the SIR model, which is susceptible, and then I is infected, and then R is recovered, but then we had to also put in D for death. And so this is basically a disease evolution model of how disease goes through a population. It's partial differential equations. What we had to do was figure out how can we do this on a quantum computer. So the goal over here was to find an optimal lockdown schedule. And I'm actually going to go forward a little bit just to show you the result, and then we'll go back. So what we're looking for is, as the disease in a city or area increases, we don't want the hospitals to get overwhelmed, so we want to shut down that city. But overall, we don't want to shut every city down, because that will affect people's lives and the GDP or the economy. So we want to keep cities open that don't have as much disease, but we want to shut down the cities where there's a lot of disease. So this is what we were looking at. So in this paper, we looked at the partial differential equation, which is the disease evolution. We looked at the transmission rate between different cities. So this becomes a quadratic problem. You've got disease moving between cities. It's going up in some cities and then evolving into other cities. And interestingly, there's a discussion over here from Lucas and then from Alexander that this problem can be solved as a knapsack problem. So we looked at the knapsack formulation, converted that problem into the knapsack QUBO, and that knapsack QUBO, it's very easy to put that on D-Wave. So basically, we let the disease evolution evolve classically. So the partial differential equation is evolving classically. We stop it like every week or every month or whatever. And then we look at how much disease are in the various cities. And then we use the knapsack problem over here to do an optimization to figure out which cities should stay open, which cities should be closed, or the ones that are closed, if they should be opened up again. And you can see the results over here. So you've got different cities, and initially they're all open, then some begin to get shut down. Some remain open, and I think the model over there is trying to maintain some sense of economy or GDP. But then at day 25, or whatever the sampling is, all of them have been shut down. Then they open up a little bit, then they shut down. So the system is basically trying to optimize between the different scenarios. If there was no lockdown, the disease evolution would basically go through the whole population. But with this balanced approach, you can see that the disease kind of goes up, and then the cities shut down. So then it starts going back down again. Then it's opened, it goes up. So they all kind of go up and down a little bit like that. And you can also see the same thing happens with the hospital bed capacity. If there was no lockdown, it would be very detrimental. But with the optimization, there's some balance that's kept between all of the different cities. Okay, so that was a different example. Let's see. Okay, so sorry, there's a question here about Harmony versus ARIA. Harmony is IonQ's older ion trap. It's 11 qubits. And then ARIA, there was an ARIA 1, now there's an ARIA 2. These are 25 qubit ion traps. And you'll see, as you saw, ARIA 2's results are pretty good. So it's a high fidelity, high quality system with 25 qubits. And they call them 25 algorithmic qubits, but so now let's go on to the next step over here. We've got C, which is going all the way up to the D-Wave CQM and BQM models. Those can handle 500,000 to 1 million variables. So when we're dealing with real world problems, and again, these are binary variables. So we have to take the real world problem, convert it into some kind of a binary problem. And when you start doing that, you really need a lot of variables. So it really helps when you can go up to 500,000 or 1 million over there. So in this case, with ZebraCat, we worked on this optimization problem where we are minimizing the holding cost, purchasing cost, transportation cost. And what we're trying to determine is where should we order inventory and what schedule should we order the inventory on. So it's a complicated problem. It has a lot of variables, and I'm just going to quickly show the equation. This is basically the equation. There's the equation for the ordering costs, holding costs, purchasing costs. We have to convert all of these into binary variables, and then there's constraints on that. So all of this has to be put onto the system. Basically, you can imagine that we've got multiple suppliers, multiple retailers, we've got multiple items moving back and forth. And then in the end, the system is able to predict how often each retailer over here is ordering items. So these are different items. This is the order schedule. Some items are being ordered every day here. Some are every 2 days. Some are every 4 days. And so every retailer is different because they have different demand. And we also include pricing in here. So let me see if there's if I can find where the price is. This C is the cost, the purchasing cost. So depending on how much you order, you have a different price breaks. So if you order more, you get a lower price. So that does change this, how each of these function. What we found over here is that as we increase the number of retailers, products, and suppliers, as you can see, is go from trial 0 to trial 5, there was very quickly, there was a tipping point where the classical solver, which is Groby that we use over here, which is in blue, took much longer to solve this problem than if you use the D-Wave hybrid CQM. So D-Wave hybrid CQM pretty much takes the same amount of time, while the classical took much longer. The main reason for that is these quadratic terms. These are bundling or interrelationships between items, or between the item and retailer, or between items and suppliers, or bundling discounts. Purchasing behavior would be like if you order one item, you also order another item. So which two items should be ordered from the supplier together versus which ones should not. So these interrelationships is really what the quadratic terms that makes it very easy for D-Wave to solve the problem, but hard for the linear programming solvers like Groby to solve the problem. If you don't have these quadratic terms, it's just fine to use Groby. Okay, so we also did sensor placement. This is in ZebraCAT. We were optimizing in an energy company, where should we place sensors. The common model used is a particle swarm optimization problem. We were able to take that problem, convert it into an objective function. And what our goal is to, we want to cover this area with sensors. And of course, if there's a wall that blocks the sensor, and we want to use some minimal amount of sensors to do maximum coverage. So we were able to basically convert this problem into the CQM model. And then, here's an example of a result where we have different sensors placed in different locations, trying to optimize the coverage. The green is where the sensor is covering, and yellow is where the sensor is not covering. Okay, so just in summary, you can see that at the low level over here with the gate quantum computers, we can do problems that are less than 40 binary variables. This is an area still where a lot of R&D is happening. We have to improve our algorithms, error correction, and of course, as these devices improve, they'll be able to solve larger and more complex problems. In the B category over here with annealers, they can solve about 140 or less variable problems. Great for solving quick optimization problems, toy or model problems. And then finally, getting closer to real world problems, maybe prototyping real world problems where you can convert your variables into 50,000 or 100,000 binary variables. You can use things like the CQM or BQM model that's available in D-Wave. These are not obviously quantum, but they're hybrid solvers, but they do a great job. Okay, so that's the end. Open to questions.
Awesome. Thank you so much, Alex, for speaking with us. Unfortunately, we are out of time. But thank you everyone for joining the webinar today. And next week, we actually have another webinar called Growing Good in Government by Building the Feedback Loops of the Future. So if you're interested in watching this webinar, be sure to register on the website. And I hope everyone has a great day. See you next time.
Thank you.
Thank you.